My name is Julio Tino. I'm the Dean of the McCormick School of Engineering and Applied Science. My only job here is to pass the mic to Kevin Lynch, who will be running the event. Kevin is the director of the Center for Robotics. But I just wanted to welcome everybody here. This is a very diverse audience, and I think this will be educational for most of you. By the way, speaking of diverse audience, is there anybody from the Art Institute here? Okay, you. So we'll meet in there, okay? If there is any, I need to give a tour to these people, separate tour. So we are delighted to be able to do this, which is the official unveiling of the Institute of the Center for Robotics and Biosystems. And Kevin Lynch will introduce the panel, and there will be a presentation that hopefully will set the tone for everything that happens. So again, many thanks for joining us here today. Thank you.
Thanks, Julio, and thank you all for coming to the launch of the Center for Robotics and Biosystems. My name is Kevin Lynch. I'm the director of the center. And today we're going to give I'm going to give a brief introduction to the center, and then we're going to follow that by a panel on our future with robots, and we'll talk about that a little bit more later. Now, before I get started, though, I want to make sure to thank the many people who helped make this happen. I had no idea that launching a center was so involved. So thank you to the people who put together the website, Krista, Katya, and Tanisha, the video and graphics and marketing team, Kyle, Julie, Alex, Alexandra, and Nathan, and of course to Amy for putting together this event. I also have to thank our funders. Some of them are listed here. There's many others who really keep the wheels turning. And then of course McCormick and Northwestern for being so supportive of what we're trying to do here. The support we've gotten in terms of space and other things has really made this center a reality. So I want to start by showing a video that provides an overview of what the center is about. You can find this on our website, and it's just maybe a week old at this point. The Center for Robotics and Biosystems focuses on research, education, and public engagement in the areas of robotics, human-machine systems, neuromechanics, and bio-inspired systems.
My particular interest is in the sensing behavior of animals and how we might build robots that can adopt some of these sensing strategies that animals have.
I'm primarily interested in physical human-robot interaction, where the human and the robot are physically interacting with each other and physically affecting each other.
One of the most important goals of the center is to learn from each other, to bring people with different expertise together in the same space so that they can share ideas and achieve synergies that wouldn't be possible otherwise.
Northwestern is a truly interdisciplinary environment. We have a large, open, collaborative space where students can interact, and I think the close integration with the Master of Science in Robotics program is really good.
There's just a lot more opportunity for the space to act as an incubator, not just an incubator for academic ideas, but also an incubator for entrepreneurial ideas, an incubator for what we should be doing in the future, even if it's not what we're doing right now.
Our work on human-robot systems benefits greatly from our close collaboration with the Shirley Ryan Ability Lab.
What that means for me as an engineer is that I have unparalleled access to clinical expertise because we're actually situated in the hospital and we interact with these patients every day. They're around us all the time. We can also see where our patients are struggling and where our technology would hopefully help one day. And we want that to get to them quicker.
I personally feel very fortunate to work with such a talented, diverse group of faculty and students who are so passionate about their research and education.
I think that the center and the set of interactions that the center will bring with it should mean that 5 years from now, we can look back and see lots of the big ideas being produced at Northwestern in robotics really started as a function of these small interactions. That type of work is going to be more likely than it has been in the past.
Our future with robots is inevitable, and so it's really about planning for that future, making sure that the benefits of robotics are shared, and think about how we should co-evolve together for the benefit of mankind. Okay. So that's the center. The center is a place. It's a space where we can collaborate and share resources. But more importantly, it's an idea. And even more important than that, it's a set of people who collaborate with each other. So the idea is in our mission statement here, we're basically working towards a future where humans and robots can collaborate seamlessly and safely, where our robot designs are inspired by biological principles, and where our robotics work actually leads to breakthroughs in our understanding of neuromechanics. So in summary, what we're trying to do is we're focusing on the science and engineering of embodied intelligence. So the people, the most important part of our center, come from 4 different departments in McCormick, as well as the Feinberg School of Medicine and the Shirley Ryan Ability Lab. The core faculty do much of their research in the space that you'll have a chance to see later at our open house. And then we have affiliated faculty, people that we work with, and people that have access to the center space. So a little bit of history. We actually at Northwestern had a significant impact on robotics before it was even a field. In the mid-50s, Jacques Denevit was a PhD student here working with Professor Dick Hartenberg on the kinematics of mechanisms. Basically, how to describe the configuration of an articulated body or mechanism or robot. And usually you need 6 numbers to describe the position of a rigid body in space, X, Y, Z, roll, pitch, and yaw. But they determined that if they're jointed, that you can get away with a minimum of 4 numbers to represent the configuration of every rigid body in a mechanism. And those 4 numbers came to be known as the Denevit-Hartenberg parameters, or DH parameters. And they are enshrined in every robotics textbook, introductory robotics textbook that any of us have ever learned from, including me. A little bit more of our recent history. In the late 80s, Michael Peshkin and Ed Colgate arrived, and there they are looking very youthful. And they joined forces almost immediately. The 2 of them came together and joined to make the Laboratory for Intelligent Mechanical Systems. And it was really that 2-person seed around which the entire robotics effort has grown here to what it is today. Over the years, we added more faculty in the area of robotics. And in 2012, we added a new wing in the BC infill, now called the Willens wing. And with that, we created the new Neuroscience and Robotics Lab, and LIMS was retired. Another major milestone was in 2014 when we instituted the Master of Science in Robotics program. And then now with the dedication of our new space in the AB infill and with other faculty joining the effort, today we're becoming the Center for Robotics and Biosystems. So what do? Research, education, public engagement. And research, of course, is what I'm going to spend a lot of our time on today, but I do want to spend some time on education because it's something that the faculty in the center are very passionate about. And I'm going to just call out a few highlights here of educational innovation coming out of the center. And these first 2 are coming from Michael Peshkin. So when he started teaching electronics, he thought about how to escape the tyranny of the lab that's fixed in time and space. And he came up with the idea that, well, students all have laptops these days. You know, they're very powerful computing devices. We let them bring them to class. I'll give them a kit of electronics, and we can do electronics together in real time instead of the traditional lecture and then the 3-hour lab later. And a lot of us have adopted that since then in other departments too. But one thing that made that possible is the invention of the N-scope here. So this is a portable oscilloscope that hooks up to your laptop. Under $100, Michael and 2 of his students developed successful Kickstarter. Now it's a commercial product and it's being used by other universities around the country. Another thing that Michael did, which a lot of us benefited from, was create the Lightboard. So the Lightboard is something that makes it easy for you to create video content to put online for education. And I am one of the beneficiaries of that. I've generated hundreds of videos using Michael's Lightboard. We have an online specialization in robotics on Coursera that students all over the world are taking, and other courses online in addition to other educational videos made using the light board. And then, of course, the most significant thing we've done in education is under the leadership of Todd Murphy in 2014, we developed the Master of Science in Robotics program. Been very successful. Many of our students are out there now, contributing to companies based on their 15-month experience in the MSR program. So our dedication to education has been recognized in a number of ways, but maybe most significantly, half of our core faculty have received the top teaching award at the university. So let me move on to research. So we can categorize our research into 4 basic themes: bioinspiration, neuromechanics, and neuroscience, human-machine systems, swarm robotics and decentralized computation, and general autonomous robotics, which is kind of a grab bag of everything else that doesn't fit in those first 3. So let's start with bioinspiration, and in particular, the work of Professor Mitra Hartman. So she and her colleagues have been studying animal whiskers. So many animals have whiskers, and not all of them can actually whisk actively, but some can, like rodents. And so this rodent is learning about its environment by actively whisking its sensors back and forth, using the contact information to build up a model of the environment, and can do that in dark places where vision is no longer a useful sensory capability. So one reason that whiskers are a really interesting model system to study if you're studying the brain is that the sensory processing is relatively simple. So after the mechanoreceptors at the base of the whiskers receive a signal, it goes through only 2 stages of neural processing in the brain before it comes back out as motor activity to drive the muscles that drive the whiskers. And Mitra's group is working to understand all phases, basically from the input to the output. And here's an example. What you see here is a motion capture of a real rat whisker as it's being deflected, and then a neural recording in the brain from stage 1. And so you can see here, as the whisker is being deflected, start getting spikes from the appropriate spot in the brain. Okay, so Mitra's group is basically mapping out this entire sensory motor pathway. And so that's the basic study, the basic science that the group is pursuing. But then they're also pursuing applications of this in robotics. So up here in the left, you can see an artificial whisker making contact with an object, and then the voltage readings you get from strain gauges at the base of the whisker. And then the question is, how do you interpret that information that you're getting back to tell you what's in the environment? Next to it, you can see a robot arm with a 5-time scale rat head on it that's being used to explore the environment, to build up a sensory model of what's in the environment, perhaps a point cloud. And so the strategy for moving the robot arm and moving the whiskers together to gather that information. And if you split that voltage signal into high and low frequency components, you can actually not just get the shape of an object that you're interacting with, but also its texture. And whiskers can be used for other things besides contacting solid objects. It can be used for detecting air or wind flow by, for instance, aquatic mammals. So here's another model system, the black ghost weakly electric knifefish. And this is the object of study by Professor Malcolm McIver and his colleagues. And this is a really interesting fish, both for its method of locomotion as well as for sensing its environment. So here you can see the black ghost moving back and forth by sending traveling waves down its ribbon fin, this long fin that runs down its belly. And based on whether the traveling wave is going one direction, the other, or there's 2 waves meeting destructively, creating a jet upwards, this same ribbon fin can create thrust in many different directions. And you can contrast that with a typical fish that wags its tail and goes forward. This fish goes backwards and forwards equally easily. So the Navy is very interested in this as a method for propulsion. It's very silent, and it creates a highly maneuverable vehicle. And so this work, funded by the Navy, is on developing an underwater vehicle that actuates its fin rays. In this case, I believe there's 32 in this device. But depending on the traveling wave sending down the ribbon fin, you can move backwards or forwards. Now, the next version of that is even more impressive. It's got 64 motors running down its belly to actuate that fin ray. Now that fish is approximately omnidirectional. It can move in any direction at a given time. And because of that, it needs a sensory capability that's complementary to that. So this fish has co-evolved its locomotion and sensory capabilities. You and I are basically designed to operate in front of us. Our eyes are faced that way, our hands operate out there, we're good at walking forwards. But since this fish can swim backwards, it needs to be able to sense behind it also. So let's develop this omnidirectional sensory system called active electrosense, where the fish creates an electric field between its head and its tail that alternates 1,000 times a second. It has voltage sensors spread out all over its body. And anything nearby that has different electrical impedance than the water will generate a signal on those voltage sensors. So here, a piece of food nearby is creating a hot spot. So again, the Navy is very interested in this as a sensory modality. Underwater vehicles tend to have sonar, which are very good at long distances, but not good close by. So complementing the highly maneuverable fish using the ribbon fin, now we've got an artificial electrosense system where the electric field is created between the head and the tail, and a small number of voltage sensors are spread out over the surface of this sensor pod. And now you can do things like navigate amongst obstacles without any other sensory modality. So here you can see the sensor pod being driven by a robot. It doesn't know anything about the obstacles in the environment, but those PVC pipes have a different electrical impedance than the water does, and it picks those up with its electrosense. So this sensory modality is good out to about a body length or so. So it's complementary to those long-range sensing capabilities like sonar. And you can also put this electrosense capability on other things besides a submarine. So here's a robot hand intended for underwater use. And when the robot gets close to an object, the electrosense capability will pick up the location of the object and be able to use that for grasping. One more exciting project out of Malcolm's lab also has to do with the sensory capabilities of animals. So a theory that has come out of his basic studies into the fossil record is that when fish came out of the sea, our ancestors first came out of the ocean, they evolved larger eyes. And those larger eyes allowed them to see at great distances on land. The utility underwater is less because the light doesn't travel so far, but on land, it's important to be able to see far. And so in this very amusing video, one of our top videos on our YouTube channel, it's got a better narration than I'm giving you right now. You should check it out. So the fish the impulse to get out of the water is because there's all this food available on land if it could only get it. So the eyes are a big part of that. And now, with this increased sensing range, it becomes important to plan, right? So if this fish decides to go straight towards the thing it's trying to eat, well, maybe it's going to escape. But if it's able to plan to go around the sensing range of the prey, they'll be more successful. So now the sensory capability is driving the evolution of cognition. So this is something, again, that Malcolm's lab is studying. So moving on to human-machine systems. Cobots were invented here at Northwestern. So cobots are one of the hottest areas of robotics, how to make robots and people work well together. And Ed Colgate and Michael Peshkin in the mid-90s coined the term and developed the first cobots. So they were working with GM on how to assist workers that are doing difficult tasks like attaching a car door to a car frame. But they wanted the process to be safe. So one way to make an assistive robot is to have it amplify your muscle power. But if something goes wrong, it's possible for that robot to be very dangerous and injure you. So they came up with the idea of how to make a robot that's mechanically passive, but still able to provide assistance. And this is what they called a Cobot. So the idea is that this operator is still moving the door around. They're still providing the motive force, but the wheels down here are actually steering the motion to provide very precise placement of the door onto the frame. And so this is a video of one of the very first Cobots here in our lab. And it's hard to see, but the wheels down here are basically steering and guiding the user. And with that, you can do things like create virtual funnels. So you can start out by moving the door freely, but as you get closer to the car frame, it's going to funnel it into place for you. That same idea can be used to generate a number of different possibilities. Advanced prosthetics, like we'll see later, or in this case, a haptic interface. So a haptic interface is the idea where you are able to feel a virtual world. Instead of just seeing it, instead of just hearing it, you're able to feel it. And the usual approach is to take a robot arm, attach an instrument to it, and let the user, like a surgeon, move that instrument around so that when that virtual instrument touches the virtual tissue, I'm able to feel the force feedback through the robot. They were able to use the Cobot idea, again using steered joints in here to create very high fidelity haptic feedback, able to create stiff surfaces that are unable to be created by a typical haptic interface. But for haptic interfaces, you don't have to just hold on to a robot as an intermediary between you and the virtual world. And again, Ed and Michael have demonstrated this with haptic touchscreens. So we've all got one of these in our pocket, and usually we interact with it by looking at it and using our finger as input. But what if the screen could give you physical output too, tactile output? And so they've developed a new technology where basically as you slide your finger over the surface of your touchscreen, based on the location of the finger, they can either turn on electroadhesion using a capacitance effect to pull your finger against the screen or to let it go. And as you do that, as a function of position, you can actually feel textures on the surface of your phone. So there's a touchscreen like this in our space, and so after the panel, please go and check it out. As I mentioned before, the Cobot idea has also been used to make an advanced prosthetic working with RIC. Now it's the Shirley Ryan Ability Lab. And we've had a number of projects with Shirley Ryan over the years, and we continue to grow that collaboration. One that I've been involved with is creating a neuroprosthetic for people who've suffered a spinal cord injury. So these people don't need a mechanical prosthetic because they still have their musculature, they have the bones, they haven't had an amputation, but they've lost the ability to send signals from their brain down to control their arm. So working with Eric Perot and Matt Tresh and others at the RIC and Case Western, we worked on an FES neuroprosthetic. So the subjects who suffered the spinal cord injury have a surgery to implant a stimulator pack in their abdomen that goes to electrodes to stimulate the muscles of the chest or the shoulder or the back. And by stimulating those muscles, you can cause the arm to move. Now what we want to do is we want to pair that stimulation capability with a brain-machine interface so that when this person who's suffered a high spinal cord injury wants to reach out and grab a piece of food, they can do that on their own without having to have a caretaker help them. So the experimental setup looks like this. The subject is holding on to a robot arm, and while we drive their arm around with the robot, we can also stimulate their muscles and then feel what forces are being created against the robot. And with that, build a model of how we need to stimulate the arm to cause a particular motion. And so the end result of that, so what you see here, this is a top view of a subject being pushed around by a robot arm. So this is during the calibration phase or the system ID phase. During this, we're also stimulating the muscles to find out what their contribution is. And then after that, we turn off the robot. It's still attached, but it's put in free mode, so it just floats along. And now all of the motion of the arm that you see here is due to stimulations that we're providing to her muscles. And then you can take away the robot, and then this is simulating sort of a simple reach out and grab activity. This is Brenna Argall's work. So Brenna has a joint appointment in McCormick and Feinberg in the Shirley Ryan Ability Lab. And she's working on shared autonomy. So the idea is that you have somebody operating a wheelchair, but that person may have a motor impairment that affects the sorts of commands that they're giving to the wheelchair. So why not give the wheelchair some ability to sense its own environment and some intelligence itself so that you can share the autonomy between the human and the intelligent wheelchair. So there's a lot of ways that you could do this, and Brenna and her group have been studying the relative advantages of different ways of sharing autonomy with the wheelchair. And one of the things that they've found is that people's preference is highly personal. Okay? So you can work with 7 different subjects, and the way they prefer to interact with their wheelchair may be different for every one of them. So as part of that, they've come up with a paradigm whereby they can customize that assistance working with the subject. And what you see here in this example, this subject is using a 6-joint robot arm with a spoon to try to reach out and again do a simple activity of daily living. But they're operating a low degree of freedom input. So they can't directly control all the motions of the hand of the robot arm. So what he has to do is he has to every now and then change the mode of the robot by pressing a button, right? But if you work with that subject to develop a customized interface, now you can take away this time-consuming mode switch and make the interface much more usable for the patient. This is another example of human-machine systems. This is by Todd Murphy's group. So here the idea is to enhance the situational awareness using drones flying overhead. So imagine you're walking down a street, you're looking for something, but you also don't want to be surprised by what's around the corner. So you've got these drones flying overhead and relaying information back to you. And the question is how to create an intuitive interface now so that the user has an enhanced sense of where they are in the world and what dangers or what other things might be out there. We also work in swarm robotics and decentralized computation, and we've all seen examples of this where fish flock to protect themselves against predators or geese fly to save energy. Here's ants that are bridging a gap by using their bodies essentially as the bridge building material. And then termites can collaborate to build giant structures that obviously no single termite has blueprints for, but together with their collaboration, they're able to build very complex structures with interior architecture to them. So the question is, how can we build robots that are simple? Each one of them is simple, but they can perform complex tasks. This is work of Mike Rubenstein. He's showing us that using 100 robots with very simple control laws, they can collectively perform tasks that would be complex to perform centrally. So each robot is running its own individual control law, and it's only talking to nearby robots. And with the right program, they're able to do things like you see here. Take an input shape that you want them to form, and over time, just through their interactions with local neighbors, never seeing a big picture of the entire shape, they can create the Northwestern N. And you can see this in the open house if you come after the panel. So the question is how to automatically take something like this and turn it into a program. You can use that same idea for other applications. Working with the Navy, we've come up with decentralized estimation and control algorithms. This work is joint with Randy Freeman. And you can do things like infer networks from just observing the behaviors of the individual nodes in the network. Now, this is kind of an Orwellian example where Big Brother is trying to figure out who's talking to whom. But there's lots of examples in economic networks or power grids where it'd be important to understand how one agent is influencing another. This is recent work from Todd Murphy's group where they're using very simple collective robots that really can't do much by themselves. So each one of these little guys is a robot. They call them smart particles or smarticles. And so if you put it on the floor, all it does is kind of thrash around. But if you put them near each other and enclose them properly and let them learn about the interactions that they have with each other, then over time you can come up with these emergent behaviors where the robots can cause their enclosure to rotate counterclockwise or clockwise or translate. So the idea here is how do we make intelligent or smart algorithmic matter when you have a lot of these small building blocks, you can get some interesting behaviors out of them. Last topic I want to mention, general autonomous robotics. So again, this is the catch-all. So we do a lot of work in robot manipulation. And when you think about robot manipulation, you probably think about things like you see here on the left. And we do work like that on multi-finger manipulation and tactile sensing. But there's lots of other kinds of manipulation. I want to show this example. So here's a few washers sitting on top of a vibrating platform. And this platform becomes basically a programmable conveyor belt. And depending on how we vibrate, we can create vector fields on the surface of the platform that cause the objects to move in different directions. So the plate's vibrating at about 30 hertz, and you can't really see it moving much, but you can see the effect of friction with the objects. So our work on manipulation looks at more traditional ideas of manipulation as well as graspless manipulation. And one more bit of bio-inspiration, animal locomotion on complex terrain. So everything you see here is an example of terrain where robots can't go now, right? Basilisk lizard running on water, mountain goats over there. We've got an elephant shrew here showing us how it can walk on soft ground. And then we've got this red fox here that can either pad along on top of the surface of the snow, or when it wants to, it can dive into it to get its prey. So this is work with Paul Umbenhauer, and it's about trying to understand how to design robots and their control strategies to interact with soft, yielding, and complex terrain. So obviously the shape and the compliance of the foot matters, how you program it, its intelligence, its control. And the idea is that by studying animals, we can build robots that embody these kinds of principles. So here's an example you can also see when you come to our open house. So this is simple one degree of freedom robot. All it does is it moves up and down. And here you can see it hopping on sand. So these are actually poppy seeds, very loosely packed poppy seeds. And the robot is just continuously jumping on the sand. But the interesting part is how, and I don't think you can see it well because of contrast, is how it interacts with the sand. So here's a little bit of a close-up. Here's a leg that's just falling right onto the sand, but it's stiff. So this is, you falling onto a soft sandy beach, but keeping your leg and your knee locked out. You just kind of drive right into the sand and you penetrate far. But if you put a soft spring in there, and here it's simulated, the depth of your penetration becomes much less. And this is the cat's landing strategy when it bends its leg and absorbs the energy. So what we're interested in is understanding the interaction here between the foot and the ground, and then designing control strategies to allow efficient locomotion. Okay, so that's just a quick summary of things that we're working on in the center. You can come see our research afterwards. We have an open house, and this is where the reception will be. Lots of good food and drink there. But the students have worked hard on their presentations over here, too. So please try to make your way through and come to see the interesting work being done in neural robotics and evolution of foresight. So I just want to close by saying the center is firmly rooted in McCormick, and we have strong collaborations with Shirley Ryan Ability Lab and Feinberg. And much of what we do is the science and the engineering of robotics and bio-inspired systems. But one of the purposes of establishing the center and having this event today is trying to reach out to other parts of campus. Okay? Clearly, our future with robots is going to be determined in a large part based on how we decide questions of ethics of using robots in the military, whether we allow self-driving cars on the street, and then who's responsible when there's an accident. What it means to have robots in our home, collecting data on us all the time and assisting us. So privacy issues, ethics issues, policy issues, these are all things that are important. And one of the purposes of the center is to try to begin to establish some of these collaborations with other parts of campus. We really want to see our connections traveling out to the rest of the university. And so with that, that's one reason that today's panel is on our future with robots, to try to address some of these issues beyond just the technology that I've talked about for the most part. And we have a very distinguished panel here today. And I won't say much about them because in the interest of time, but if you got your programs on the way in, there's a lot of information about our panelists. So with that, I will turn it over to our moderator, Rob Walcott, and we'll set up the chairs. Great, thank you.